All right, so Assalamu alaikum. Today we're going to discuss the band structure of graphene, and through graphene, we'll open up the doors to a large variety of honeycomb lattices, a large variety of two-dimensional structures, which are currently one of the most important areas of investigation in condensed matter physics. So let me share my screen. All right, so today, as I've mentioned, we're going to talk about graphene. So this is lecture number 23, I suppose, and our topic of discussion is the band structure of graphene. So why have I chosen this subject? It's because graphene presents a very nice example of tight binding in two dimensions. Graphene has a honeycomb structure. The lattice comprises a honeycomb, a regular periodic arrangement of hexagons with carbon atoms lying on the vertices of these hexagons. Similar structures could be silicene, toluene, plumbine. Even though the atomic sizes are different for those materials, graphene is somewhat the simplest in a sense. If I have alternate boron and nitrogen atoms, we'll get the famous boron nitride. We can also form other materials such as phosphorine and so on. So let's look at the band structure for this material. Now, in order to look at the band structure, we really need to know what is the lattice here and how many points are there in the lattice. Now, if I consider one of these atoms, suppose I consider this atom over here. If I look at the environment of this atom, which I call I have 3 carbon atoms coordinated with A. And just look at the environment of A. There is a bond to the top and 2 bonds that are flanking downwards. On the other hand, consider another kind of atom, B. Now, in this atom, the environment is totally different from A. And I can partition all the atoms inside this structure into 2 kinds, A and B. So each unit cell really comprises 2 atoms. So it's like a diatomic chain of atoms when we were considering the diatomic, when we were considering the tight binding model. So a similar formalism would apply to this scenario as well. All right, excuse me. All right. So now let's imagine that this structure is subdivided into what are called 2 sublattices. There is an A sublattice and there is a B sublattice. And the structure is formed by the interpenetration of these 2 substructures. And I have to look at the environment of A differently from the environment of B. Even though the atoms on A and B, they have the same self energies, they are absolutely identical. Both of them are carbon atoms. So this problem is partitioned into 2 subspaces. An A subspace and a B subspace. So if I look at A and I would like to find out the neighboring molecule, the atoms to A, so I can define, in a sense, so let me define these three. So let's start with B. So I can define these three directions: A1, A2, and A3. And let me, for the sake of compliance with my notes, let me call this atom A, and let me call this atom B. So if you look at A is surrounded by three neighboring carbon atoms, which are displaced by three position vectors A1, A2, and A3. Likewise, B is also separated out from neighboring A type of atoms by three vectors B1, B2, and B3. And if I define my axis in this fashion, there's an x-axis and there is a y-axis, then I can find out what these vectors are going to look like. So I know that in a hexagon, I have different kinds of angles and so on. So if I look at vector A1, suppose also that the distance between two adjacent atoms is A. So vector A1, you can find out that it's going to be equal to A, and the two elements in the position vector are under root 3 by 2 and 1/2. Likewise, A2 is A minus under root 3 by 2, 1/2. A3 would simply be A 0 minus 1. So these are the three position vectors, A1, A2, and A3, and I'm defining my position vectors in this strange notation that A1 really is A under root 3 by 2 half. So it's a column vector, but for shorthand, I'm just writing them as these row vectors. Likewise, I can define B1, B2, B2, and B3. So if I look at B1, this position vector here, B1 is turning out to be the negative of A2. B2 is turning out to be the negative of A3. And B3 is turning out to be the negative of A1. So I can write B1 as the negative of A2, means A under root 3 by 2 minus half. B2 I can write down as the negative of A3, A01, and B3 I can write down as the negative of A1. So I've partitioned my atoms into two classes, A and B. All the A atoms are interlinked with the B atoms, and all the B atoms are interlinked with the A atom. So in the tight binding model, there are orbitals on A and there are orbitals on B, and an electron that exists on an A atom can hop and transition or tunnel into B kind of atoms and vice versa. And what I'm trying to do now, I'm trying to look at what does a typical neighborhood environment for an atom A looks like, and what does a typical neighborhood environment for an atom B look like. And then I find out the neighboring position vectors. And then I would like to associate tunneling parameters with these position vectors. And this is something that we've been doing for the tight binding model. So if you look at the tight binding model and we write down the Schrodinger equation for the different kinds of atoms, the two kinds here are the A and B kinds. we can construct a matrix, and from the matrix we can find out a characteristic equation from which the dispersion relationship pops out. And this is exactly that we would like to do here for this particular example. So in most textbooks on graphene, they approach this problem with the easier method, which is the method of the second quantization. And they use creation and annihilation operators and Fourier decompositions um, of functions. Of course, we're not going to do that because we haven't studied this in this course. So I'm going to just teleport what we've done for the two diatomic tight binding chain to the example of graphene. So let's march on. So if we use our what we've learned from tight binding in the diatomic chain, I have two classes, A and B kinds of atoms. And the good thing is that the self energy for an electron existing on A and B is the same. Let's call it simply E naught. All right, so if I were to find out a trial solution and project it onto an A atom, and then I would project it onto the B atom, I can get two simultaneous equations. And by extension to what we've learned so far in the diatomic tight binding model, our equations look like the following. So what we see is that if I have E naught, I can find the function C. Now the C is defined by the position vector Rm. Instead of M and N, I need to define the position vector Rm, which is the location of the Rmth atom. And it's suppose it's of the A kind. So I have a term that includes the self energy for an A kind of atom. And then I need a tunneling parameter, which I know it almost always looks like minus T. And then I have a string of Dirac delta functions followed by C, R, N, and I want to integrate over Rn. And if I assume that nearest neighboring interactions are possible, then my Dirac delta functions look like delta Rn is equal to Rm. So if I'm on an A atom, I'm here, I can go to a neighboring B atom by this route or by this route or by this route. So interactions are possible when if I have a position vector R M N, sorry, and I have another position vector which is Rm. A hopping is possible when Rm minus Rn is either A1, A2, or A3. So exactly the same argument would let us write these positions, Dirac delta functions in this form. Rm plus A1 plus delta Rn Rm plus A2 plus Kronecker delta Rn Rm plus A3. All right, and this must equal to the total energy CRMA. Now remember that the CRMA and CRMB, these are the wave functions. So this is one of my equations, and with the help of the Kronecker delta and the sampling theorem, I can simplify this in the following fashion. E naught, the self energy. So as in all tight binding problems, I have a self energy term and I have a tunneling term or a hopping term. And I assume that the amplitude of hopping is given by minus T. For this, you need to recall your understanding of the tight binding model. And you can always look up my previous lectures on this subject. So E naught CRMA minus T. By the way, this is B because you're connecting A with B here. Minus T, and then if I were to take the sum over all Rn's, and I'm going to pick up particular values of Rn's, which are equal to Rm plus A1, Rm plus A2, and Rm plus A3, I'll end up with CRM plus A1 atom B plus CRM plus A2 atom B, CRM plus A3 atom B. This equals E CRM atom A. So this is my first equation. But exactly the same approach, I can write down the other equation. E naught CRM atom B minus T CRM. Now instead of A1s, I have B1s because the atom B's are connected to the A's through the B vectors. So here I have A CRM plus B2 B atom A plus CRM plus B3 atom A. This equals E CRM atom B. This is my second equation. Now I need a trial solution for this. All right. And the trial solution goes as follows. So my ansatz is now that C, any vector D on atom A has some amplitude. Let's call that amplitude alpha EI K dotted with D. Likewise, C, any displacement vector D on atom B is given by another amplitude B EI K dotted with D. Now, if I insert these CDs A and CDs B in here, I will get a sequence of equations. So Rm appears on both sides of the equation. So it just gives a common exponential factor on the left hand and the right hand side, and it just cancels away. So I'm going to skip this step, and I'm going to rewrite equation number 1 after insertion of the ansatz as E naught minus T EI K dotted with A1 plus EIK dotted with A2 plus EIK dotted with A3 equals E. That's my equation number 3. E naught minus T EIK dotted with B1 plus EIK dotted with B2 plus EIK dotted with B3 also equals E. And of course, there are the appropriate factors here: alpha here, beta here, and an alpha here, a beta here, and an alpha here, and a beta here. Now I can put this in matrix form, and I'll end up with E naught minus E, EIK, I goes from 1 to 3, and EIK P1, BI, where I goes from 1 to 3, E naught minus E alpha beta gives me 0. Now, if I need to solve this for alpha and beta, I can always do that. But what I could also do, I can find out the energy eigenvalues. And those energy eigenvalues are found out by diagonalizing Hamilton, this term. Let's diagonalize this. But we also note that EIK dot with B1 is simply equal to e raised to power minus I k dotted with ai, because all the bi's are inverses of any one of the bi's. So welcome, Bilal. Right. So now what we're going to do is we are going to put this slightly different version in here, and we're going to, and remember that we know what k is. K is some kx, ky, and we have all the a's and the b's in front of us. Here they are, all the a's, all the b's. And I can always find out the dot products between the k's and the a's. So all of these terms can be explicitly written down. And eventually, if I were to diagonalize the Hamiltonian, the characteristic equation that would be formed would be of the following kind: E naught minus E minus T E I A K x under root 3 by 2 plus Ky under root 2 plus E I A minus Kx under root 3 by 2 plus Ky by 2 plus E minus I Ky. Likewise, the term here will simply be the complex conjugate so if I write down the complex conjugate of this term, I'll get A minus IA Kx under root 3 by 2 plus E minus IA minus Kx under root 3 by 2 plus Ky by 2 plus E I Ky epsilon naught minus epsilon. I need to find out the determinant of this, and I need to equate this to 0. This is my characteristic equation here. So if I do all my multiplications, so I'll get E naught minus E square. And if I carried out all the multiplications and I did the algebra, I really need to take the modulus square of this term, because this term is related to the other diagonal term by complex conjugation. My final result turns out to be something very illuminating, which is, let me write down the final result. I will get 3 plus 2 cosine of 3 a kx plus 4 let me write down the final result. Okay, let's do one step further. 4 cosine a over 2 under root 3 kx cosine of 3 over 2 a ky. Now I can simplify this further using trigonometric expansions, which would I can expand this cosine term in terms of a cosine square term using this formula, that cosine cosine of 2 of something is cosine square of theta with a 2 minus 1. So I could use this expression and write this as a cosine square term. All in all, at the end, I will get E naught equals E naught plus minus T, and in a square root factor, I'll get 4 1 plus 4 cosine square under root 3 over 2a plus 4 cosine of a over 2 under root 3kx cosine of 3 over 2 aky. Of course, all of this the algebra I've skipped. All of this algebra you need to do yourself. So let me recap here for the sake of Bilal. What we've done is, Bilal, we've taken this honeycomb lattice in graphene, and we've noticed that there are two kinds of atoms. Both of them are carbon atoms, but two kinds in the sense that these atoms exist in two different types of environments. An A atom has a triangular environment and the B atom has a triangular environment, but the two environments are inverted with respect to one another, right? So A has a carbon atom immediately below it, whereas B has a carbon atom immediately above it. So we define the environment of A because an electron on atom A can hop to an orbital on atom B, and we need to find out what routes can it take. So we define three vectors, A1, A2, and A3, and these are shown over here, these atoms, these position vectors. Likewise, atom B has three neighboring vectors for atoms of the kind A, and these vectors are B1, B2, and B3. And they happen to be inverses of any one of the A's. So now what we would like to do is we would like to write down the Schrodinger equation. We come up with a trial wave function, which is a superposition of orbitals A and orbitals B, and then we project it onto an orbital A, and then we project it onto an orbital B and get two kinds of equations. One of those equations is of this form. Like any other tight binding equation, it has a self energy term and it has a hopping term. The self energy term is self evident, and the hopping term, notice that there are Dirac delta functions. Now the Dirac delta functions are indexed by position vectors instead of simple indices, because we have a two-dimensional structure. In this two-dimensional framework, there are two position vectors, Rn and Rm. And the hopping will only take place when the displacement between Rn and Rm is either A1 or A2 or A3. And that's what these three Dirac Kronecker deltas represent. Likewise, I can write an equation for B, and then I have these trial solutions for pseudo spins or sublattice A and a trial solution for sublattice B. And then I insert the values into my two Schrodinger equations, and I'm left with a matrix equation. And a matrix equation is some term acting on the wave functions, the coefficients of the wave functions yielding 0. And if I need to find out the energy eigenvalues, I take my matrix, put it in determinants and equate it to 0. I'll get a characteristic equation, and then I solve that characteristic equation to find out the dispersion relationship. So Bilal, is this recap clear?
Yes, sir. Perfect. Thank you.
Okay. So now if I look at this dispersion relationship, looks very daunting, but this is the band structure. This harbors all that you need to know about the band structure of pristine graphene, pure graphene without any impurities. So I can also plot this band structure. Of course, it's going to be a two-dimensional reciprocal lattice indexed by vectors kx and ky. So I can, if I were to plot this, let me see how I can plot it. And I plotted it for you already in Mathematica. Excuse me. So let me share my screen appropriate fashion. All right. So here is the Mathematica file. So what I've done here is I've defined my vectors A1, A2, and A3. Let me try loading this in into one node so I can take notes on this. So excuse me just a minute. So insert. Let me see. Just a minute. Just a second. All right, so probably I'll need to go there over. That's never mind. So here I've defined my position vectors A1, the B's. I've defined my K, and I've defined my matrix. And I written it in matrix form over here. Okay, so this is exactly the matrix that I wrote for you in my OneNote. And then I solve for the determinant equal to 0, which is the characteristic equation. And I'm left with the forms that I've already written for you. I've simplified them nevertheless in my handwritten calculation. And this is what the structure looks like. There are two bands. One band is with the positive sign before the discriminant, and the other band is the negative sign before the discriminant. So with two atoms per unit cell, or with two sublattices, I get two bands. One is an upper band and the other is a lower band. Sometimes they're called positive and negative bands. Sometimes they're called conduction and valence bands. And these bands have a flower-like structure. And the nice thing is that these bands touch at certain points. All right. And they will touch when whatever is there in the square root is equal to 0. Because then the upper and the lower bands are going to meet at a certain point. And we're going to discuss that when I finish off this Mathematica exhibition. So this is what the band structure looks like. All right. A blue band is the upper band and the yellow band is the lower band. And I can do contour plots for these bands as well. And these are what they look like. Okay. So this is for, I think, the lower band or the upper band, and this is for the lower band. One remains positive, the other remains negative. The chemical potential is right in the middle. And at certain points, which I call the Dirac points, these bands are going to meet. And there are two Dirac points in the first Brillouin zone. And we're going to locate these points in a minute. So this is what the dispersion relationship looks like. So let me go back to my OneNote now. What I need to now find out is where are my Dirac points? So these bands meet right? These bands meet at certain points. And there are two distinct points in the K space. Let's call them capital K and K prime. So if you look at the dispersion relationship, so first of all, let me draw these bands in a, so I have a two-dimensional pattern and I could just stretch them out and the bands are going to meet at certain points. So this is just a 1D cutaway from a two-dimensional pattern. These bands are going to meet at certain points. I actually like this. Okay, so there is a valence band and there is a conduction band, and these bands are slightly different, but at certain points, which are called the Dirac points, K and K prime, they are going to meet. All right, and we'll find out what the behavior of these bands is in the vicinity of these so-called Dirac points. But how do we know that these points exist? These points will exist when the two bands have the same energy value, when they overlap, and that's going to happen when everything that I've written in this everything. So when I do that, I can locate what is kx and ky. So I can put 1 plus 4 cosine square under root 3 over 2 akx plus 4 a over 2 cosine a over 2 under root 3 kx cosine of 3 over 2 aky. I can put this equal to 0. All right, so excuse me. Excuse me, just want to check my notes here. Right, so and let me just give me a second, please. Okay. So how do I find out? Now I have one equation which is some trigonometric function of kx and ky, and I want to put this equal to 0. So I can come up with some trials. What I could say is that suppose that this term here equals half. Right, so if this term equals half, then this term equals 1 by 4. So I'm left with 1 plus 4 into 1 by 4 plus 4 over 2 cosine of 3 over 2 aky. This means that this is 2 plus 2 cosine of 3 over 2 aky. Now, when is this term equal to 1/2? This term is going to be equal to 1/2 when cosine of 60 is 1/2. So a over 2 under root 3 kx is pi over 3. This means that kx is pi 2 pi over 3 under root 3a. So we would like to see whether this particular value of kx will lead to a solution for ky. So let's see. So this makes us cosine of 3 over 2 aky minus 1. And this is going to happen when this term here is equal to pi. And when that is the case, ky equals 2 pi over 3a. So if I have this pair of values of kx and ky, I would note that the two bands are going to meet at this point. So I call this the capital K point. Capital K point will be given by, in the reciprocal space, 2 pi over a, 1 over 3 under root 3, 1 over 3. So at this point in the K space, we're going to have the two bands touching one another. Likewise, if I were to put this value to be equal to minus 1/2, then kx and ky can still be found. Kx will then be minus of this, but ky will remain unchanged. So I'll get another k point, which is called k prime. that K prime is going to be 2 pi over A minus 1 over 3 under root 3 1 over 3. So I have these 2 points at which the bands meet. Now, if I look at the reciprocal lattice or the hexagonal lattice, it's also going to look like a hexagon. And if I drew the first Brillouin zone in that hexagon, so this is my first Brillouin zone. This is the center, the K equals 0 point, which is generally denoted by gamma. I have a point here K, and I have a point here K prime. So look at, so K and K prime are these points here in the K space, and this represents the first Brillouin zone. And we observe that the bands meet here at these K and the K prime points. They're also going to meet here, but these points are not distinct. So these points are related to one another by reciprocal lattice vectors. So they're not distinct points. There are only two distinct K points inside the unit cell, inside the first Brillouin zone. So the bands are non-overlapping everywhere, but the direct band gap structure is such that at these precise Dirac points, they're going to meet. All right, and we've found out the locations of these K points as well. And the next thing that we could do, so any questions about this, Bilal?
सर यहाँ पे जो हमने k की वैल्यूज दी हैं तो we just took some arbitrary value for one of the terms in the bracket, तो हमने उसको half के minus half लिया, लेकिन we can also choose it as some other value. इसको हम 1 भी कर लेते, इसको 1/3 कर लेते, तो we would have also obtained some values for kx and ky.
So what we need to do is you need to find solutions of these equations. So if you insert some other values of kx, so instead of 1/2, you got 1 or 1/3, you'll also get other solutions, but then you'll have to look at solutions that are inside the first Brillouin zone. All right, so you'll get solutions, of course, in the second, third Brillouin zone, but all of them can then be mapped back into the first Brillouin zone. All right. So these are the only two distinct solutions that you'll get inside the first Brillouin zone. Okay.
Makes sense.
Because the different Brillouin zones, the second Brillouin zone can be partitioned and brought back into the first Brillouin zone. All of them have the same area. So here we're looking at the reduced zone scheme in other words, which are the K points modulo 2 pi over A, modulo the reciprocal lattice vector. Okay?
Yes, sir. Thank you.
So now what we could also do, so the really nice thing is that these bands in the vicinity of these Dirac points, and why are these called the Dirac points? Because I'll show in a minute that this looks like the Dirac equation in 2 dimensions. So these bands near the Dirac points, they have a special relationship with respect to K. They're linear with respect to K. Generally, in electrons inside metals or electrons even inside semiconductor bands, you have dispersion relationships that are somewhat parabolic or quadratic. Here you have a linear dispersion relationship, which is easier to engineer, has lots of fascinating electronic properties. So what we could really do is find out the structure of these bands in the immediate vicinity of the Dirac points. Now, how do we do that? Well, if I look at this Hamiltonian here, so if from this equation I would like to write down a Hamiltonian, that Hamiltonian is the following. Some E naught, which are on-site energies, and it's going to be the same for the two kinds of atoms, and a minus T and some delta here, and a minus T and some delta star here. This is what my Hamiltonian looks like for graphene, right? So where delta is, excuse me, where delta is given by the sum of E I K dot with AI 1, 2, 3, right? So this is my Hamiltonian. Now, if for the time being these two diagonal terms are the same, I can put without loss of generality, put this equal to 0 so that the two bands meet at 0 energy. So then my Hamiltonian looks like this. Okay. And in that case, these two terms are complex conjugates of one another. I can write this Hamiltonian in terms of Pauli matrices as well. All right. So this will become -2. And then cosine of K and since I have I plus iota, so I think minus iota sigma x Pauli operator, sigma y Pauli operator. So the Hamiltonian can always be expressed in this fashion as well. All right. So is this making sense? So sigma x, if I define sigma x to be 0, 1, 1, 0, sigma y to be 0 minus iota, iota 0, I expand this as cosine of KAI plus iota sine of KAI. I will immediately find out this expression for the Hamiltonian in terms of the Pauli operators. All right, and I can readily find out the eigenfunctions and of course the eigenvalues as well. So is this all making sense? Now what we would like to see is what happens in the vicinity of the Dirac points. So suppose I take the capital K point. So I know what the dimensions of this K, what the coordinates of this K, they are given by this thing here, 2 pi over A. So this is my K point. So let me just reconfirm. Yes. All right. So what I need to do is in the vicinity of the K point, suppose I take my, I define a vector Q in the K space, which shows the location of my K point and its displacement from capital K. So I'm close to the capital K point, but slightly away by a distance Q. So Q is my displacement from the Dirac point. Okay, and now I'm writing my K. This is position in the K space as this small k, and the capital K is my Dirac point. So now what I need to do really is I have my my dispersion relationship. So I could take my delta. So yeah, so my delta, which is the sum of E I K dot A I can expand this, right? I can convert it from polar into the trigonometric form, and this turns out to be, after you do the algebra, excuse me, this turns out to be a ky over 2 cosine of a kx under root 3 over 2 plus E minus I 3A over 2ky. This is my delta. Now, what I could do, I could use the Taylor series expansion and find out what this function looks like in the vicinity of capital K. So in order to do that, I would need to find out the following. I need to find out the gradient of this function. So I need to find out this term, and I need to find out this term. And when I find out these terms, the change in delta, so in other words, how does delta change if I go from the capital K point to some point nearby in the K space? That change is going to be given by these derivatives multiplied by Qx plus this derivative multiplied by Qy. So this is simply the lowest order term in the Taylor series expansion. And in vector notation, this is simply the gradient of this thing, which we've defined over there in the K space, computed at the K point, capital K point. So we really need to compute this at the capital K point, multiplied with the vector Q. Okay, so the change in some parameter is given by the gradient of that parameter multiplied by the amount of change in the parameter space, right? So this is just shorthand for the change in any function is given by the gradient of that function computed at some base point, and then I take the dot product of this thing with the change in my parameter. So let's call that parameter Q. Okay, so this is how I define the change in any parameter. Take the gradient and multiply it with the vector that defines the change in the parameter. Okay. All right, so if I were to take this term here and find out the gradients, I can always do this by hand, but Mathematica can also do this for me. So I've done that over here. So, all right, so here I've defined my what I've seen, what I call capital delta. I put it as M here. I define my K points, the K capital X and KY. And then I also define my K prime points, by the way. And then I differentiate my function with respect to Kx and then compute it at the K points and the K prime points. And eventually, so if I insert all of these values in here, eventually, and this is something you could do it on your own. Excuse me. The delta at the K point my delta is going to be approximately given by minus 3 by 2, approximately because it's just the lowest order expansion, the Taylor series A, E, I, excuse me, Qx minus I, Qy. All right, so this is my new delta in the vicinity of my K point. All right, and I've so this is at the K point, and likewise at the K prime point, my delta A is going to look like 3A over 2 I pi by 3 plus IQY, right? So this is something that you can do on your own. It's just algebra, and I've formulated or outline the process by which this is achieved. So if I look at the Hamiltonian at the K point in the vicinity of the K point, in other words, my Hamiltonian is going to look like minus 3 over 2 a I pi by 3 0 0 qx minus iqy and qx plus iqy. And of course, there's a minus t as well, which gets multiplied to give me t. Now, this is a global phase factor. I can ignore this. Global phase factors in Hamiltonians don't really matter. So I'm really left off with at 3 over 2 and if I were to find out the eigenvalues of this function, that is really simple. So what the eigenvalues are going to look like? First of all, let's write the Hamiltonian terms, the Pauli operators. At 3 over 2 sigma x plus qy sigma y. All right. So in shorthand, I can write this as q vector dotted with the Pauli operator vector, where the Pauli operator vector is defined as having terms sigma x and sigma y as its elements. So this is exactly what the Dirac Hamiltonian looks like in 2 dimensions, which this q is replaced by a momentum operator. This is the Dirac Hamiltonian in 2D, which is generally observed for relativistic particles in high energy physics. So that's why graphene is like a toy model for high energy physics experiments, something that you need really particle accelerators to achieve. You can actually do it on a piece of graphene which is stripped off from a piece of scotch tape. You take a carbon pencil, lead pencil, put it on paper, and have a carbon scotch tape, press it on the lead pencil and extract. You'll exfoliate a layer of graphene on it. So you don't need to build a particle accelerator. You can see the same physics, the same high energy physics, relativistic physics, with the help of these particles, which are now called Dirac electrons in the vicinity of the K points. And that's why these points are also called the Dirac points. So this term here, so there is some velocity here. This term here plays the role of a velocity. It's called the Fermi velocity. And you'll notice that the Fermi velocity depends upon the spacing between the two carbon atoms of the order of 1.2 angstroms and the tight binding parameter T, the hopping parameter T. Okay. And if I were to look at the dispersion relationship, you just take this Hamiltonian and diagonalize it. And if I were to diagonalize it, I'll get 3 AT over 2. Find out this. So let me define qx plus qy by this vector. Sorry. Let me define qx plus minus iqy by, let's call it q. Now this gives me 3at over 2 e square minus q mod square e square e square equals 2. By the way, sorry, I need to take care of this thing as well. Yes, sorry. All right, so my energy, you will observe here, is proportional to Q. And Q is the distance away from the K point. So the bands are linear with respect to. So if I were to plot this dispersion relationship, so this is my capital K point, this is my K x-axis and my K y-axis here. The dispersion relationship is going to look like, it's going to be linear here. As I go along in K x and K y, the energy goes linearly. So it's like two cones touching one another, and their tips are intersecting at the Dirac points. And likewise, I'll have a similar relationship at the K prime point as well. These 2 points, by the way, present another degree of freedom, and it arises because of the two kinds of sublattices. This degree of freedom is generally called value. I have a K value and I have a K prime value. And just as I have the spin of an electron, the spin of the electron can be into azimuthal projections, plus half and minus half, and it presents a degree of freedom for quantum information processing. Valleys also present another degree of freedom. So the valley behaves like a fictitious spin, a spin half particle with 2 degrees of freedom. And this emerging field in which we don't use the charge of an electron or the spin of an electron, rather these valleys which are inside the band structure is called valleytronics. And so graphene is where the entire discussion of valleytronics starts. And then you can impose magnetic fields. These structures become quantized according to the Landau principle. You'll get the interaction of light with these objects and so on. So I think I wanted to discuss graphene, especially in this course. And that's what I've tried to do today. So are there any questions?
सर जस्ट स्मॉल क्वेश्चन, ये जो ऊपर आपने ई स्क्वायर की ये जो इक्वेशन है इसको मैनिपुलेट किया है, तो आई डोंट, ये यहीं पर एग्जैक्टली बस ये जो है ई स्क्वायर इज इक्वल टू 2 बाय 380 क्यू स्क्वायर, तो ये किस तरह से यहाँ पे एक स्टेप किस तरह हुआ, आई डोंट अंडरस्टैंड इट।
कौन सा ऊपर
लास्ट
जाऊं?
नहीं सर, नीचे यही वाला जो है, ये फाइनल स्टेप आपने जो इक्वेशन लिखी है ना, नीचे 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 बिल्कुल नीचे ले जाए, ये जो है ई स्क्वायर इक्वल्स 2/380 मोड स्क्वायर ऑफ क्यू, ये इक्वेशन यहाँ पर किस तरह से आई ऊपर वाले स्टेप से।
अच्छा, यार मैं थोड़ी सी गलती कर दी है. So I made a small mistake. So my equation is 0 380 over 2 q 380 over 2 q star, right? This is my equation. This is my alpha beta equals 0. My equation, right? Now what I need to do, I need to diagonalize this. I form the diagonalization means I find out determinant, right? I put this equal to 0. ये clear है बिलाल?
यस सर, ठीक है।
ठीक हो गया? तो अब ये आ जाएगा e square equals shorthand for this, is right? So is this making sense now?
यस सर, ठीक है, थैंक यू।
All right. All right. So I think this will be the last lecture of this course. And I'm going to upload this, and please attempt homework number 8. And if you or anyone would like to meet me, I can always keep office hours and I can arrange meetings before the final exam.
सर, थैंक यू।
ठीक ठीक है बिलाल, शुक्रिया, बहुत शुक्रिया।
हाफिज़।
हाफिज।